Okay, now I want to move on to talking about a finer class of decidable problems. So I'll focus now on problems that we can actually do. And I want to focus on how quickly I can do different problems. And what's really neat about this is in theory of computation, we're going to get to talk about algorithms, something really important about algorithms that I couldn't introduce in data structures because you didn't have the background. But now that you know this, I've gone through the pain of learning all this stuff about Turing machines. There are things that I'll be able to tell you that are really fundamental. So let's start again by talking about Big O. I've already had you watch a few videos in Big O, and we've talked about it in class, but I just want to review the formal definition here. So Big O is a notation and concept for upper bounding the time complexity of an algorithm. So the formal definition is actually it's just about functions, but we use it in this context often to talk about timing functions that say how long an algorithm takes in terms of an input size. So the formal definition is a function fn is big O of a function g of n if there exists a constant c greater than 0, so that for all n greater than some other constant m, I'll say m sub c, f of n is less than or equal to that constant times g of n. So this makes it sound harder than it is. But intuitively what it's saying is I can scale g up so that eventually it will completely beat f on every input. So kind of in the limit. So eventually, or really in the limit, it will completely beat f on every input. Okay, so looking at an example here, I could say, what if f of n is equal to, let's say maybe n plus n log n, and g of n is equal to n to the 3/2 power. And so it turns out it's actually true that in this case fn is big O of g of n. And so I'm going to show you a visual proof of this for a second. I wrote some code here ahead of time. So here I wrote down f, and then here I wrote down g. Oops, I need to define my constant c. Okay. Now, so what the formal definition of big O is saying is if I plot f and I plot g times some constant, in this case I'm just making the constant 1, it's saying that eventually that constant times g will overtake f. And so g dominates f in that sense. I can make it happen even faster if I make the constant larger. So if I made the constant 2 here, then actually it looks like it dominates from the get-go. So that's why I indexed this constant m sub c by c. This m sub c is the point beyond which this pulls away. So here it pulls away at 1. When the constant's 1, that constant times g seems to pull away at around 13. So what this says is actually n to the 3/2 power dominates n plus n log n. Another example I could give you is this example of, let's suppose I sort a bunch of pixels in an n by n image, and then I average the x-coordinate for the smallest 10% of them. So this is something I might do. Oops, let me move my head up here. This is something I might do for some reason. And so now let me bring it into a practical setting where I can come up with a timing function. So fn now specifically represents the number of operations that I have to do in this. And if you study algorithms, you know that to sort n times n objects, it'd take, well, it's always the number of objects times the log of the number of objects for comparison-based sorts. So that would be n squared log n squared. And then if I was averaging the smallest 10%, that would be plus 0.1 times n squared over, oh yeah, just 0.1 times n squared. So there's my timing function. Actually, one thing I'll do to simplify this a little bit is I'm going to take out, by rules of logs, the log of n squared is actually just equal to 2 times the log n. So I'll take the 2 out front there. And so that's an equivalent statement. All right, so here's my claim. The claim is that Fn is big O of n squared log n. Now, it doesn't look like it would be upper bounded by n squared log n. In fact, it looks much bigger than that, right? It's 2 times n squared times log n plus this 0.1 times, so it's got more stuff going on here. So if I were to try this out here, and I were to make this n squared plus n log n, or plus, actually it would be 2n squared. So I'll just take 2n times log n plus 0.1 times log n. And then I'll make my g just be n squared times log n. So when I look at these, it certainly seems like the blue is beating the orange. So I can't get my g to upper bound my f. But all I have to do is make this constant a little bit bigger. Let's try 3. So actually, the constant 3 will do it. And why did I choose 3? Actually, let me change this to a log base 2 here, because that's what we use in sorting. And that's not going to do anything. That's just going to be a multiplicative constant in front of these. So the relationship is exactly the same. But anyway, okay, so with the log base 2, what I can say is if n is greater than or equal to 2, then log base 2 of n is greater than or equal to 1. So that implies that if I go back and I take my f, let me take this version here. If I take my f, then if n is greater than or equal to 2, then I can just multiply this term by log base 2 of n. So let me put the log base 2 here. And so I'll take this original equation and just multiply that and 0.1 times n squared by log base 2 of n. And so then I can say, because log base 2 of n is greater than or equal to 1 past that point, then I can say that the original expression is less than or equal to this. And then I can just combine like terms. And I can say, okay, f of n is less than or equal to 2.1 n squared log base 2 of n. And that is, now I have my g. So I have some constant 2.1 times g. And this is given that n is greater than or equal to 2. So that's great. What I found, so in other words, if I go back to my definition that I had, what I'm saying is I found a constant, 2.1, and then another constant, m sub c. So c is equal to 2.1 and m is equal to 2, satisfying the definition. So actually, let me go up and see if that's true. If I'm, if I make it 2.1, then yes, supposedly past 2, it's going to beat it, and you can see that's happening. If I zoom in a little bit here, let me say plot.xlim, let's see, maybe between 1 and 4. Actually, let me just, okay, it got the y limit messed up here, so I'll just go from 1 to 5, maybe. So yeah, I was saying certainly past 2, you can see it pulls away. All right, that's all I needed to show. So there's a practical example that shows that, so what, why is this practical? Because what I'm saying is, look, the dominant behavior of this algorithm to sort a bunch of pixels and then to average the x-coordinate, the dominant cost is actually for the sorting. The sorting is the dominant term, the n squared log n squared term here. This 0.1 n squared doesn't do much in the limit. It doesn't do much to control the scaling behavior of this. So I can just pretend that that 0.1 n squared is even more expensive than it is and kind of fold it into the higher order term. That's how I want you to think about a big O. So at the end of the day, we walk away with, two takeaways. Number one, the dominant terms dominate. So the dominant terms are the ones that we use to create our g of n, right? So I looked at this and I said, well, yeah, the dominant term here is n squared log n squared. That is going to grow faster than this n squared. The other takeaway is that constants don't matter. So somehow the fact that this was 2n squared log n didn't matter. I would still say that 2 doesn't really matter. Somehow the upper bound here is still n squared log n, up to a constant, we would say, when we're trying to understand the scaling behavior. So I don't want to say constants don't matter, because if this program took a day to run, I wouldn't be too happy if you could get it to run in a day. But then I said, oh, but if I was a little more careful, I could have had a constant of 1 instead of a 2. And said, well, 12 hours is much better than 24 hours. So it does have practical implications, but when we're trying to understand how the runtime grows, then this is all that we care about. Okay, so I just wanted to go over the formal definition of big O again. For my data structures class, I have this build your own definition where I show that that's the definition of big O, but you can tweak these things a little bit. If I were instead going to lower bound the function, so to say that there's a function that I can always multiply by a constant so that it's always less than or equal to my f, that's called big omega. Let's go back to big O for a second that we were just looking at. If I change this for there exists a constant c to for every constant c, I get something little o, something called little o, and that actually means that g completely dominates f. There's not even an equality, so you can think of it like a strictly less than. And then there's an analogous thing if I flip that sign, which is little omega. So I'll link this and you can have a look at it. I talked in class a little bit about little o, and little o is useful because we can use it to show complexity hierarchies. Because I can say, well, actually, if one function is completely dominated by the other one, it means that the limit of the quotient so if fn is completely dominated by g, I can rework that definition to say that the limit of the quotient of fn over g of n is equal to 0 as n equals infinity. And the important thing here is that the limit as n approaches infinity of any polynomial p over a polynomial q, where q is greater than p, is equal to 0. So we say higher polynomial powers completely dominate lower polynomial powers. So here, like n squared versus n cubed. N cubed will just completely dominate n squared. So that ratio will go to 0 as n gets larger. The other thing that's good to be aware of is that the linear grows faster than log. So that's something I can prove using L'Hopital's rule. And here's the one that's really important for us now in theory of computation, which is that any exponential, regardless of the base, will eventually completely dominate and grow faster than any polynomial to any exponential. So it's like saying 2 to the n will eventually beat n to the 10th power, even though n to the 10th gets a head start. And so here's a plot of that. Actually, in a log plot, these grow so fast I had to change the y-axis a little bit. So yeah, you can see that, and that's actually an inductive application of L'Hopital's rule here. And so this is a really important thing. Somehow an exponential is bad from the perspective of algorithms because the exponential will completely dominate a polynomial. And then you can also prove that actually the factorial is even worse than the exponential. I have a little proof here using Riemann sums. I'll link to that and you can look at it if you'd like. And here's a couple exercises down here that you can try if you want to practice your chops with the definitions. But at this point, I'm okay if you walk away with the take home here. And also the idea that exponential is much worse than polynomial. Somehow that is a different class of algorithms. And I'll have kind of a different definition that captures that moving forward. All right, so that's it for big O in general for now. But now I'm going to start thinking about big O in the context of Turing machines. And so I'll have a video on that in a moment.